Welcome to Yaka Digital Network. Today, we are tracing the physical path of electricity from the moment it leaves a massive power station to the second it registers on your home's prepaid meter. This is a major power generation site, like the Karuma or Bujagali dams. Electricity is produced here at a moderate voltage, but it often needs to travel hundreds of kilometers to reach the people who need it. Sending electricity over long distances introduces a specific engineering challenge: cable resistance. If we transmitted raw electricity at low voltages, we would need a very high current. As this formula shows, power loss is proportional to the square of the current, meaning a high current would turn a massive amount of that energy into wasted heat. To solve this, we use a step-up transformer to increase the voltage. This causes the current to decrease significantly. Because the loss depends on the square of that current, even a small reduction in amps leads to a massive saving in energy. This relationship between voltage and current is the primary mechanism that allows a national electrical grid to deliver power to distant towns and villages efficiently. Before power enters your neighborhood, it must be made safe for domestic use. A local pole transformer performs a final step-down, reducing high voltage to a standard 240 volts. These transformers use cores made of thin, insulated slices of iron called laminations. Without these, the changing magnetic field would create eddy currents within the iron itself, generating enough heat to melt the transformer or destroy its efficiency. Inside the home, your house is wired as a parallel circuit. This setup ensures that every appliance receives the full 240 volts, and that turning off one device doesn't cut power to the others. Safety depends on three specific wires. The live wire brings the current in, and the neutral wire provides the return path. The green and yellow earth wire is there for protection. If a fault causes an appliance's metal casing to become electrified, the earth wire provides a low resistance path for that current to flow safely into the ground. That surge of current instantly melts the fuse, breaking the circuit. We always place the fuse on the live wire, so that when it blows, the high voltage supply is physically disconnected. If the fuse were on the neutral wire, the device would remain live and dangerous even after the fuse had blown. Proper wiring doesn't just protect the appliance, it is designed to isolate the user from the high potential energy source during a fault. Understanding how you pay for energy is important. Prepaid Yaka meters act as integrating meters. They constantly multiply voltage, current, and time to calculate your total energy consumption in kilowatt hours. Let's try a calculation. If you run a 2,000-watt electric iron for 2 hours, and the cost is 800 shillings per kilowatt hour, what is the total cost? Pause the video now to find the answer. First, convert power to kilowatts. 2,000 divided by 1,000 gives us 2 kilowatts. Next, multiply the power by the time to get 4 kilowatt hours. At 800 shillings per unit, your total cost for those 2 hours is 3,200 shillings. While an appliance's power rating tells you how much energy it uses per second, it is the total time it stays on that ultimately dictates your bill. For a final challenge, consider an appliance rated at 240 volts and 1,500 watts. To keep it safe, would you use a 5 amp, 10 amp, or 30 amp fuse? Using P equals IV, we find the normal operating current is 6.25 amps. A 5 amp fuse would blow instantly. A 30 amp fuse is far too large. It wouldn't break the circuit during a fire. The correct choice is 10 amps, the next standard size. Remember, high voltage saves energy by reducing current. Bills are calculated in kilowatt hours, and fuses belong on the live wire for total isolation. To explore more physics and access materials for all classes, visit the Yaka Digital Network website. Keep learning, and we'll see you in the next lesson.